session of the day. This is about proofs and SNARKs. I will introduce the first speaker, who is Nan Wang, and he will talk about flash proofs, efficient zero-knowledge arguments of range, and polynomial evaluation with transparent setup. This is a work from Nan Wang and Sid Chow. And Nan Wang is online, and it will give the talk. If you can share the screen, maybe we'll see it. Yeah.
Hello, can you hear me?
We see the slides and we hear you well. So I leave the,
Okay.
Yeah, I leave you to present.
Okay, thank you. Hi, this is Nan Wang from the Australian National University. Thanks for having me. Today, I'm going to present our paper, Flash Proofs, Efficient Zero-Knowledge Arguments of Range and the Polynomial Evaluation with a Transparent Setup. We use flash proofs because our arguments run fast in verification. Let me briefly provide some notions of the zero-knowledge argument of knowledge. A zero-knowledge proof allows a prover to convince a verifier of the truth of a statement without revealing any secret information. An argument is computationally sound proof that no probabilistic polynomial time provers are able to deceive the verifier into falsely accepting it. More formally, given an NP language L, a prover aims to convince a verifier of knowing a witness omega for a statement U belongs to L. Zero-knowledge arguments should satisfy three properties: completeness, soundness, and zero-knowledge. Completeness means a prover can convince a verifier if the statement is true. Soundness means a prover cannot convince a verifier if the statement is false. Zero-knowledge means the argument does not reveal any other information except the statement is true. Flash proofs are three-round sigma protocols under the discrete logarithm assumption with a transparent setup. They do not require any computationally expensive pairing operations. Flash proof consists of two types of arguments: a range argument and a polynomial evaluation argument. The range argument aims to prove that a committed value x lies in a specific range. For example, we can prove x is in a range between 0 and 2 power 32 minus 1, or between 0 and 2 power 64 minus 1, without revealing what x is. The polynomial evaluation argument aims to prove that two committed values x and y satisfy a public polynomial relation without disclosing what x and r are, what x and y are. For example, we can prove a polynomial relation y equals x power 64 plus 1. And sometimes we only want to hide x. So we can prove that x is a root of a public polynomial equation. A sigma protocol is an efficient approach for constructing honest verifier zero-knowledge proofs. It is a three-round interactive protocol between a prover and a verifier. Before the protocol, both parties share a common input U. The prover sends an initial message M in the first round.
None, I think we don't hear you anymore.
Sorry, okay.
Oh, can you repeat the last 30 seconds maybe?
Hello, can you hear me?
Yes, now we hear you. We don't see your screen anymore.
Okay. Sorry. Okay. A sigma protocol is an efficient approach for constructing honest verifier zero-knowledge proofs. It is a three-round interactive protocol between a prover and a verifier. Before the protocol, both parties share a common input U. The prover sends the initial message in M in the first round, and the verifier replies with a random challenge E in the second round. The prover responds to the verifier with a message Z, and finally, the verifier can choose to accept or reject the proof based on the transcript U, M, E, Z. Moreover, the protocol can be made non-interactive and secure in the random oracle model via the Fiat-Shamir transform, which allows the prover to generate the challenge E by hashing the message M in the first round using a collision-resistant hash function. First, we present a new type of zero-knowledge range argument. We devise a new variant of a bit decomposition approach to prove that a committed value is in the range between 0 and 2 power n minus 1, where n indicates the bit length of the range. Our range argument is tailored to confidential transactions on blockchain platforms. By default, blockchain does not provide privacy, and confidential transactions can protect privacy by hiding transaction and the balance values in encrypted forms, such as commitment schemes. So zero-knowledge range proofs are necessary to prevent malicious parties from creating values out of thin air on blockchain platforms. For example, for confidential transactions on Ethereum blockchain, the transaction initiators are required to prove the transfer amount is non-negative and their encrypted balance has sufficient bounds for the transfer amount. We juggle the two crucial performance parameters of zero-knowledge proof in our range argument, the communication and the verification efficiency. Zero-knowledge proofs communication cost affects the transaction size as they dominate the whole transaction size. The verification efficiency has a great impact on how fast a transaction can be validated by miners on blockchain platforms. Our argument achieves n power 2/3 sublinear efficiency in both communication and verification. Our main contribution is that our range argument consumes a comparable amount of gas costs to the ZK SNARK Growth 16 without resorting to any trusted setup. ZK SNARK is called the succinct non-interactive argument of knowledge. Growth 16 benefits a trusted setup to achieve constant communication and verification efficiency. And it is the most efficient ZK SNARK so far, which only requires 3 pairing operations for any arithmetic circuits. Our argument also supports the aggregation of multiple arguments for further improvement in efficiency. Let me give a quick overview of the bit decomposition approach. The intuition is that if a value can be represented in binary format of length n, then it is in the range between 0 and 2 power n minus 1. Bulletproof is a popular generic purpose zero-knowledge argument in the discrete logarithm setting for arithmetic circuit satisfiability. And Bulletproof can instantiate a range argument. It employs a variant of the bit decomposition approach to achieve log n communication complexity and linear proving and verification complexity. Now, let me describe our techniques. We express the committed value y in binary format of n terms, with each term being 2 power I times bi, where bi is either 0 or 1. We can arrange these terms in a matrix with L rows and K columns. We use W to indicate the term for brevity. In the third round, after obtaining a random challenge vector E0 to EK-1 from the verifier, the prover generates a vector of random numbers R0 to RL-1 to compute the vector V0 to VL-1. The values V0 to VL-1 do not reveal any information due to the random vector R0 to RL-1. With VL, the verifier can compute an FL by subtracting VL from the sum of 2 power LK plus K times EK, which is enclosed in red frame. And we can further extend FL on the right-hand side of the equation, such that the coefficient of the EK is 2 power LK plus K minus WLK plus K. For verification, the verifier needs to check 3 equations. First, the verifier computes FL times VL. It generates a series of cross terms in the challenges on the right-hand side of the equation. The verifier needs to ensure the quadratic terms in the challenges are canceled out, which means that they are equal to 0. the prover must provide the commitments to the coefficient to the remaining terms, TKJ and QK in the first round. Then we can conclude that each coefficient WLK plus K is either 0 or 2 to the power of LK plus K. And secondly, the verifier sums all the VL. The prover must also provide the commitments to the SK on the right-hand side of the equation in the first round. The SK is the sum of the values in the kth column in the matrix. And finally, the verifier checks if Y is the sum of all the SK with indices from 0 to K minus 1. And at the bottom, the formula shows the number of required elements for our range argument. The number of group exponentiations for verification is pi minus 1. So 1K is a cubic root of n. Both communication and verification costs achieve the minimum. We also provide an optimization technique to further improve communication and verification efficiency. We can use one challenge E and generate a series of other challenges based on E. Considering the 64-bit argument, when we use the challenges E minus 1, E power minus 1, E power 4, and E power 5. The verifier just needs to ensure that none of the projected term challenges E power 10, E power 8, E power 2, and E power minus 2 would appear on the right-hand side when computing FL times VL. The benefit of this optimization technique is that some terms would be merged together. For example, E power 4 times E can be merged to E power 5. E power 5 times E power minus 1 can be merged to E power 4. And E times E power minus 1 can be merged to the constant term. At the bottom, the left table shows the values LK to achieve the best performance for different ranges. And the right table shows a comparison of our original argument and optimized argument. And our optimized argument can save 51 and 3 group exponentiations for proving and verification respectively. And it also saves 96 bytes in proof size. In this page, the table shows a detailed efficiency comparison of our range argument with the bulletproof. Our argument greatly outperforms bulletproof in both proving and verification. Our range argument has shorter proof size when the bit length n is no more than 22. The chart graph at the bottom shows the proof size comparison of 64-bit aggregate argument with increased aggregation size. For aggregate argument, bulletproof performs better than our range argument. The table shows the verification gas cost comparison of the state-of-the-art zero-knowledge range proofs on Ethereum at the same level of soundness errors. The gas costs reflect the number of computational operations required to verify zero-knowledge proofs. Our 32-bit range argument achieves a comparable amount of gas to the most efficient SNARK, growth 16. And there's only a gap of around 13 kilo gas between our 32 range argument and growth 16. And besides, our 64-bit range argument does not fall much behind. And the bulletproof consumes around 10 times the gas cost of ours. And next, we introduce the polynomial evaluation argument. Our argument builds on the work of Fire and Growth in Asiacrypt 13, and we call it BG13. We provide two zero-knowledge arguments, which are optimized for the polynomials of lower degree and the higher degree, respectively. The two arguments are essentially distinguished based on the proof size. The higher degree one outperforms the lower degree one when the degree exceeds 2 power 9. Our argument can instantiate the membership argument to prove that a committed value belongs to a public list of values. We can construct a polynomial such that y is 0 and the elements of the public list are the roots of the polynomial. And the polynomial evaluation argument can also be used in conjunction with our range argument to satisfy complex mathematical relations by using the Maclaurin series, such as trigonometric and exponential functions. And the range argument aims to confine the input x in a small range to make sure y does not overflow the finite field. And for this argument, I will not go into the technical details due to the time limit. Please refer to our paper for full details. Briefly, we leverage the quadratic term cancellation technique to make a non-trivial improvement on the BG13. And the table shows an efficiency comparison of bulletproof, BG13, and our work. The prover and the verifier efficiency is in terms of group exponentiations. Our two arguments achieve better communication efficiency than bulletproofs, but only use a logarithmic number of group exponentiations. The line chart graphically shows a running time comparison between BG13 and our arguments. We can see that our arguments present non-trivial improvement. And I will also point out that our higher degree arguments enable a significant asymptotic improvement in efficiency of communication and verification from O log n to square root log n, when multiple arguments satisfying different polynomial relations and sharing the same inputs are aggregated. And our higher degree argument use one log n field element to mask the input x, which is enclosed in the red frame. Thus, we can combine multiple single arguments with different polynomial relations and sharing the same inputs. So these field elements will be shared by multiple arguments. When the aggregation size increases, the communication cost will asymptotically approach square root log n. So the same also applies to the verification efficiency. Okay, thank you. Do you have any questions? Hello? I'm sorry, I cannot hear anything.
Yeah. No. Okay, we can take it offline. Thank you so much. Let's thank the speaker again.
Okay, thank you.
Okay, next speaker is in person. And we'll talk about improved straight line extraction in random oracle model with application to signature aggregation. A work by Yash Kondi and Abi Shalat. And Yash here will give the talk.
Thanks, Sanka, for the introduction. I'm Yash. This is joint work with Abi Shalat. Okay, so in this talk, I'm going to explore two dimensions of Fischland's transformation from Sigma protocol to an proof of knowledge. I'm going to look at applicability, and I'm going to look at computation cost. So in terms of applicability, Fischland only proved his transformation to work for certain Sigma protocols that satisfy a certain quasi-unique responses property. And this rules out a number of useful protocols, including like logical OR composition and logical OR composition and proof of knowledge of Peterson commitment and so on. There's this sort of folklore intuition that despite the lack of a proof, the transformation just works out of the box anyway. And that's something that I'll address in this talk. Specifically, you find that contrary to this folklore, there is an attack on witness indistinguishability if the transform is applied in some bad context. And we also show that through some simple randomization mechanism, we can fix this problem. The other dimension that I'm going to explore is computation cost. which tends to be the bottleneck in a lot of applications for straight line extractable proofs. And there hasn't been a lot of progress since Fischland's original work in 2005. We give a lower bound that to some extent explains this lack of progress. Specifically, our lower bound shows that Fischland is within a small constant factor of the optimal performance. And we do give some modest improvements in the general case, but we also look at a specific application in which to optimize Fischland's technique. Specifically, we consider NDSA signature aggregation and show that we can get improvements of up to a couple of orders of magnitude for parameters that are interesting in practice. So as a quick recap of what a Sigma protocol is, there's first a commitment from the prover to the verifier, a challenge from the verifier to the prover, and finally a response from the prover. Two special soundness says that given a fixed commitment and two different transcripts where the challenges and responses vary across them, an extractor should be able to deduce a witness for the statement. So the Fiat-Chimie transform is this really elegant way to go from a Sigma protocol to a non-interactive proof. Basically, the prover, instead of asking the verifier for the challenge, hashes the statement and the first message. The proof of security for the Fiat-Chimie transform comes from this so-called forking strategy. At a very high level, it means that we sort of fork the execution of the prover. We run the prover twice or a certain number of times and pick a random query that the prover made and change the response and hope that the prover still gives us an accepting transcript. And yeah, this works with decent probability. There are a number of notable advantages for the Fiat-Chimie transform. One is that it's pretty simple to describe and implement, and it's also very efficient, which makes it very attractive in practice. Specifically, proving and verifying a Fiat-Chimie compiled proof is basically the same as proving and verifying for the underlying Sigma protocol. It also comes with a couple of downsides, which we focus on in this work. Specifically, the forking strategy doesn't compose concurrently. So if you want to argue concurrent security of a NISIC that's compiled, the Fiat-Chimie transform may not work. And there is also this quadratic security loss that comes from having to learn the prover multiple times. Straight line extraction, on the other hand, is an extraction strategy that follows this sort of rough paradigm, which is in the random oracle model, we just run the prover once, take a look at all the queries that the prover made to the random oracle, and just this information should be sufficient to extract a witness for the statement. So this one-shot straight line method of extracting was proven to support concurrent composition in Pass's work. And Pass also gave a simple cut and choose construction that did achieve the straight line notion in his work. In subsequent work, Fischland gave a straight line extractable compiler that avoided some of the cut and choose logistical costs that came in Pass's work through this really nice proof of work type idea. Very roughly, this involves sending this transcript AEZ of the Sigma protocol subject to this constraint that the hash of AEZ should be equal to the all zero string. In a little more detail, Fischland's transform works something like this. The prover, as usual, begins by sampling a Sigma protocol first message, A. Then it computes in its head a response to the challenge 0. Let's call it Z0. It feeds it to the random oracle and checks the output. If it's anything but the all zero string, this is a rejection. And so the prover must try again. The prover in its head keeps incrementing the challenges and correspondingly answering them, feeding them to the random oracle and checking if it's the all zero string. And basically the prover keeps going until it finds an AEZ transcript that does hash to the all zero string. And once such a transcript is found, this is the output. So soundness comes from the fact that except with probability 1 over the size of the hash function, the prover must try more than one accepting transcript. And so with more than one accepting transcript, we're able to extract. Completeness follows when the hash function size is small. And so the prover can terminate efficiently. Because these two things are at odds. We need a small hash function for completeness, and we need a large output for soundness. And so there's a simple way to get around this, which is just by repeating this protocol in parallel a number of times. I'm not going to talk about these repetitions because for the context of this talk, it's going to be enough to look at a single instance of Fischland's transform. Really quick, if we compare Fischland's transformation to Pass, setting all the parameters so that we're comparing apples to apples with the same computation cost in both cases, the dominant asymptotic term in passes transform comes from some extra logistics that have to do with the cut and choose. Basically, think of this as some like Merkle tree revealing thing. And this extra logistical cost is like a logarithmic factor worse than the underlying Sigma protocol itself. And so Fischland's transform is nice because we avoid this extra logistical, this like cut and choose logistical cost altogether. That's the like quantitative part. And now let's look at the qualitative aspect of it. So Passes compiler is shown to work for any Sigma protocol. Fischland's compiler, on the other hand, the security proof relies on this property called quasi-unique responses. So many standard Sigma protocols do support this. Think of proof of knowledge of discrete log, for example, but there are many other interesting ones that don't, like proof of knowledge of Peterson commitment opening and proving knowledge of one or two witnesses and so on. At a very high level, the quasi-unique response property is something like this. If we were to fix the commitment and the challenge, this should also implicitly fix the response Z. That is, it should be hard computationally for a prover to come up with a commitment, a challenge, and two responses such that they're both accepting transcripts. So it's kind of easy to see why this is necessary for soundness in Fischland's compiler. Specifically, a prover who's able to violate this property can fix the commitment, fix the challenge, and just keep brute forcing on the third component, the response, until it finds one that accepts with the random oracle. And recall that in the extractor for a Sigma protocol, we need the challenge to change. That is, we need the same commitment in different challenges. But in this case, we have a prover who's keeping the challenge fixed. There's this folklore understanding that this is not because of any like inherent underlying issue, as much as just the Sigma protocol abstraction kind of getting in the way. If you were to just adjust the syntax of Sigma protocols and how the transformation works, we can kind of get around this. I'd have some discussion about this in the paper, specifically with the proof of knowledge of one or two discrete logarithms as an example. At a very high level, the intuition is that for a lot of protocols, many natural ones, if you were to fix A and E, the commitment and challenge, even if you have two different responses for the same challenge, you can still extract. Like there is still meaningful information that you get by looking at two different responses when the challenge is the same. So we, in our work, we like formalize this folklore. We add this notion of strong to two special soundness, which in addition to the original two special soundness also gives the extractor transcripts of this form, where the challenge is different, but either the challenge can vary or the response can vary. The second or part is what's new. Right, so that looks like we fixed it. But it turns out that Fischland's proof of zero knowledge also depends on quasi-unique responses, which is not very intuitive. Right? We can't see an explicit attack right away. And in this work, we show that it turns out that it's actually quite strongly dependent on this property. In particular, in the absence of this unique responses property, we can construct an explicit attack on witness indistinguishability. So we rely on the following two facts. One is that in some Sigma protocols, if you have the witness that the prover used to compute the proof, we can simply work backwards and get the entire random state of the prover. Think of Schnorr's proof of knowledge, where a response is just a linear combination of the witness and some randomness. So if you have the witness, you can just solve for the randomness. The second fact is that once you fix the commitment, Fischland's compiler is deterministic. So this lets us construct some interesting algorithms. Specifically, we can consider this following attack strategy. Given a Fischland compiled proof pi, we can use fact one to get the internal state of the Sigma protocol prover. And by fact two, we know that Fischland's compiler doesn't add any extra state on top of the Sigma protocol. And so now we have the entire state of the entire internal state of the prover. And now we can sort of recompute the proof because we have everything we need to compute the proof. And by completeness, recomputing the proof should give me back the same pi that I started out with. Now let's look at what happens if we use a different witness. In particular, there are some Sigma protocols where for the same challenge and commitment, for the same commitment and challenge, the response Z will depend on which witness is being used. So think of the proof of knowledge of one out of two witnesses, for example. If you fix A and E, the third response Z is going to be different whether you use W0 or W1. So this lets us analyze the second case. So over here, what I've highlighted is by completeness, if you use the same witness that the prover did, you get back the same proof. What fact 3 tells us is if you use a different witness than what the prover did, you get a different proof with some high probability or with some noticeable probability, some different proof pi prime. So this creates a distinguishing event. You can basically now test if a given witness was used to compute a given proof, and that breaks witness indistinguishability. Of course, the details are all on the paper. So 2 out of those 3 facts that I just showed you are inherent properties of the Sigma protocol, and we can't do anything about them. The second fact, which is that Frischland's compiler is deterministic, we can fix this because this is a compiler level thing, not a Sigma protocol thing. So basically, instead of incrementally stepping through the challenges until you find a proof, the prover now can randomly step through the challenge space until a proof that hashes to the all zero string is found. There are some subtleties, of course, but yeah, the idea behind doing this is that even if you retrieve the Sigma protocol randomness, there's some extra state that comes from the compiler that you can't get back yourself to execute this like retracing kind of algorithm. Okay, so that's what I wanted to say about applicability. Moving on, we sort of zoom out a bit and take a look at how the literature has progressed for straight line extraction in the random oracle model. There's passes feasibility result, Frischland's technique, which we just covered. And as of now, these are basically the only techniques we have. And it's natural to ask why. So in this work, we phrased this problem of random oracle query complexity. That is, how many queries to the random oracle does it take to produce a proof? So we showed that if we tighten this lower bound, asymptotic lower bound that Frischland gave in his own paper, we can derive a concrete bound that explains some interesting things. Specifically, if we have a prover who makes P queries, of which a verifier checks V of them, so this is P, this is V, then P choose V, should it be at least 2 to the K, where K is a security parameter. So K bits is security, so this is very concrete. And it turns out that Frischland's technique is nearly optimal if we consider this method of measuring things to be a metric. And yeah, when I say nearly, this presents some opportunities for more questions. So either it's a loose bound or there is some room for more improvements. And it turns out we're kind of in the latter case. So the way that one way to view Frischland's technique is that we make the prover solve a sort of proof of work problem, which is inverting a hash function using this Sigma protocol transcripts. So instead of inverting a hash function, we consider a different proof of work problem, which is finding collisions of a hash function. And it turns out that this has some nice combinatorial properties that lets you get some general improvements. So empirically, we get like 10 to 15% for interesting parameters, 10 to 15% faster to solve the same proof of work for the same difficulty level. But rather than the general case, I want to talk about an application-specific optimization, which is signature aggregation. Right, so we consider Schnorr or DSA signature aggregation in this paper. There was a previous work by Chakias, Galio, myself, and Nikolenko, which sort of did a naive application of Frischland's transform to aggregate DSA signatures. Signature aggregation, as a quick introduction, is a fairly intuitive concept. If you start with a bunch of plain signatures and run it through some aggregation machinery, you're able to get an aggregate object that captures the effect of all of these signatures, but is lighter in some sense, usually bandwidth. In this case, the cost of transmitting this aggregate signature is going to be less than the cost of a naive concatenation of these things. So let's break down exactly what the dimensions of this transformation are. Maybe I'll get to the questions later. So can I remove this somehow? Never mind. So I'm not going to get into the details of the aggregation protocol itself. I'm just going to talk at a very high level of how Frischland's transform is applied. So there are 2 dimensions in Frischland's transform. One is the number of queries, which I'm going to call TAG for the time to aggregate. And the other, which is kind of obscured over here, is the cost per query. So the number of queries and the cost that it takes to compute each query. It's a pretty intuitive way to characterize computation. And we show how to improve both dimensions. So very roughly, the query complexity, that's TAG, corresponds to the expected running time of finding a certain number of collisions of an L-bit hash function. And our insight is that for the same number of collisions, so for the same number of instances, if we change the problem to finding an R collision rather than an R inversion of a slightly modified hash function to make sure we respect the same security constraint, then the resulting thing is slightly faster to compute. I mean, it could be significant enough in practice, but it's not a huge, it's not necessarily an asymptotic improvement. This follows from some nice combinatorial analyses by von Mises and Pernille. And it turns out that this same idea translates to the NISIC setting as well. It's not just for aggregation. Yeah. And as for the cost of computing each thing, like the cost of producing each query, this very roughly, the Sigma protocol has this kind of structure. The prover has a polynomial f that encodes all the signatures. The ith coefficient of f is the ith signature. And so if you're aggregating n signatures, you have a degree n polynomial. The verifier sends the challenge E, and the prover basically has to reveal f evaluated at E. Now, we know through different parts of the literature that like evaluating a degree n polynomial is inherently going to cost n multiplications in ZQ. But in the context of Fishlin's transform, we're going to be evaluating the same polynomial multiple times and finding some polynomial evaluation that hashes to the all zero string or that satisfies the random oracle in some way. And so we can think about amortizing across the evaluations of this polynomial. This is a well-studied problem. It's polynomial multi-point evaluation. It turns out that we can't use techniques from the literature out of the box to optimize polynomial evaluation because either they're not very good concretely or the concretely efficient ones like the fast Fourier transform are not compatible with elliptic curves that we use for common signature schemes, like at DSA, for example. So in this work, we have a custom polynomial evaluation algorithm, which is not brilliant asymptotically. It is sublinear, but nowhere comparable to FFT or whatever. But it does work quite well for the concrete parameters that are interesting for aggregation. Right, so in summary, in our work, we explore this notion of witness indistinguishability and how it's not preserved by Fishlin's transform in general. And we show how to get around this problem by this like randomization mechanism. Then we also gave a lower bound that explains the lack of progress in this particular domain. We showed that we can get some modest general improvements. And if you look at a specific application, we can, of course, speed it up quite a bit. And you can find my work on ePrint, and thanks for your attention.
Are there any questions? Yes.
Hi, thanks for your talk. I have one question. Could you please show the slide with the timeline? Oh, okay. So just a quick question. Are you aware of this Tatsumata transform from crypto last year, which proposes like seems like a different way to achieve straight line extractability in ROM?
Was that the verifiable encryption one?
I mean, yeah, some kind of encryption to the sky.
Yeah. So that is an alternative paradigm. As far as I'm aware, okay, I guess that's a different. I mean, in theory, you could also have like generic, like there are generic proofs in the random oracle model alone. But I guess I was more looking at compilers from Sigma protocols to NISIC. So ideally, we wouldn't want to, for example, depend on the circuit representation of the exponentiation function if you want to look at Schnorr. Like if like we want to avoid expressing things as circuits and then like applying another transform on that. I'm not too familiar about the details of that work though, but does that?
Yeah, I see. Thanks.
Sure.
Yeah. Yes, there is also a question online, but yeah, let's take it.
Thank you for the talk. Sorry, when, for instance, you are claiming these accelerations, which units are you using for saying that is, for instance, 1.5 faster and like that? Is in the number of multiplications, or did you implement the protocol? Can you elaborate on that, please?
Yeah, so
Thank you.
that was an analytical cost. So the expected running time of finding a certain number of inversions versus the expected running time for finding like so many collisions. So that 1.5 is like the ratio between how long it takes to find inversions versus how long it takes to find collisions. And that part, so that claim was analytical, and then the like 200x stuff was implemented.
Implemented in, can you give more details?
Oh,
How do you
yeah, that
implement?
was in Rust. There's a public library for the aggregation scheme that we built on, and yeah, so we just sort of tweaked that implementation to get this.
Thank you.
Here.
Since we are already on this slide, I was wondering why the Unruh transform is not, is it not straight line extractable according to your definition?
It is, but it's basically just passes transform.
Okay, I see.
Yeah.
Question online. Are there instantiation of Fishlins technique in the standard model?
No, not that I'm aware. Because I mean, I guess FHME itself is very recent, so I don't know how you do Fishlin in the standard model.
Okay. Any other questions? Then let's thank the speaker again.
Thanks.
And next talk, it's about counting vampires from univariate subject to updatable ZK SNARK. This is a work by Janos Sim, Mihal Zayak, and Helger Lima. And Jano will give the talk online.
Thank you for the introduction. I hope you can hear me well and you can see the screen.
Yes, all is fine.
Very good. So yes, let's start with a bit of motivation, which I guess you have heard quite a bit already. So this talk is about efficient zero knowledge arguments, as all talks in this session. And basically what one wants to do in this scenario is that we want to prove something, but we don't want to leak any information. And there are numerous applications for this in the world, like private cryptocurrencies, electronic voting, where you might want to prove the correctness of tally without leaking the votes, delegation of computation, and so on and so on. And the model that we will be using in this work will be something like this. We have a prover, we have a verifier, and we have a trusted third party. And prover knows a statement X, which is public, and the witness W, which is private. And verifier knows only the statement X. And then the trusted party generates something called a structured reference string. So this is some setup key and gives it to prover and verifier. And prover can then use this structured reference string to generate the proof. And verifier will either accept the proof or reject it. In more particular, we will focus on ZK SNARKs in this work. This stands for zero knowledge, succinct, non-interactive argument of knowledge. And basically here, there is some relation, and prover claims that X and W satisfy this relation. And we require that the argument system has knowledge soundness, which means that prover must know the witness W to succeed. And we require zero knowledge, which means that only information that is leaked is that X and W satisfy the relation, but we will not leak, for example, the W. And we also require succinctness, which means that the proof size is sublinear in the size of the statement and the witness. However, there's a big problem with this structured reference string. Namely, in most applications, you don't have a trusted party. And typically, this structured reference string also encodes a secret key. So it looks something like this. Trusted party picks a secret key, then it applies some function to the secret key, and out comes the SRS. However, if the trusted party is actually malicious, then it's very easy to break the system by using the secret key. So ideally, you want some sort of a distributed SRS generation. But this is quite cumbersome in practice. So yes, so SRS generation is quite fragile. It is possible to have a transparent SRS, but then typically you also give up something in efficiency. So we still would like to have a distributed SRS generation, but there are some ways how to make it a bit more nicer in practice. One notion is universal SRS. This basically means that we can use the same SRS for many different relations, at least up to some size of the relation. And secondly, we have the notion of updatability for SRS, which means that the SRS comes with a very nice distributed SRS generation protocol. Namely, the first party can generate the initial SRS, and then the subsequent parties can update it. And the final SRS will be secure to use at least as long as one of the updaters was honest. So these are basically ways how to make the SRS generation a bit more, or quite a bit more usable in practice. So now let's go to our result in this work. We constructed the shortest universal and updatable ZK SNARK that is known so far. So here is a table comparing them. As you can see from here, the only ZK SNARK which is smaller is CROT16. However, that one is non-universal and non-updatable, so it's a lot more difficult to use it in practice. But we are also competitive in prover and verifier runtime. Maybe not the absolute best, but we think we are quite comparable. However, our SRS is more complicated than in the previous works, but still updatable and universal. So let's go to techniques, how we construct our ZK SNARK vampire. We take two previous ZK SNARKs, Marlin and Lunar, and then we construct a new sum check argument that we call count. And I'll explain in a moment what's a sum check argument. Then we use some quite aggressive polynomial patching techniques to further reduce the proof size. And then there are lots of small optimizations. And with most of these small optimizations, we also see that there's a trade-off between the proof size and prover's computation time SRS size. So in many cases, you can even turn off some of these optimizations and get slightly larger proof, but then either smaller SRS or prover's computation time. I will mostly focus on this new sum check argument in this talk, because this is technically maybe the most new thing. However, in reality, many of the small optimizations accumulate and they actually give quite a significant difference. We used R1CS light constraint system. So this was first proposed in Lunar. In more particular, let's imagine you have some relation, you have some public input x1, x2, and some with w. Then you can write your relation as a circuit. And then typically what you would do next is that you would use R1CS. And this is basically here, this circle represents pointwise multiplication. So here you basically have some matrices ABC, which represent the circuit, and then you have the vector Z, which some way represents the wires. And basically it says that relation is satisfied if this matrix equation is satisfied. But in our case, we use R1CS Lite, and this is somewhat simplified version of this. You have only two matrices which represented the circuit, and the Z still in some way represents the wires of the circuit. Now, how do you go from R1CS Lite to a sum check argument? So again, we start with this R1CS Lite equation. Then we split. And this step actually that I explained right now, this is mostly done in Marlin and Lunar. We did our own modification, but this is just to give you some context. So we split this Z into two halves, ZL and ZR. And then if you write M in this nice way and U in this nice way, then you can actually represent this whole relation, R1CS Lite relation, as simply a matrix multiplication where you have some matrix M, times a vector u is equal to 0. Now, if we index the rows and columns by some set h, and then we can interpolate m and u over this set h, such that we get two polynomials, mxy and ux. And then we can represent this matrix vector product in a polynomial form as follows. And what we do in the protocol is that we substitute this variable x by some random value alpha. And then this, what is inside the sum, you can actually write this p of y, some polynomial. And then you actually just check the R1CS-like constraints you get into this sum check formula. So basically, you have some polynomial evaluated at points in some set h, and these are summed together, and they are equal to 0. So this, maybe if you even didn't follow all the details in this transformation, it's important to note that we can go from R1CS-like to this sum check form. So if we can do the sum checking, then we can verify that some circuit is satisfied. Okay, let's go to some background first. We will be using bilinear groups in this work. So here we have 3 groups, G1, G2, and GT of some prime size G, P, which generates P1, P2, and PT, and we're using type 3 bearings. So this means that there's no isomorphism between groups G1 and G2. We will be using additive notation, and we will be using bracket notation. Namely, it means that when we want to write A times P1, then that's actually equal to A in bracket with subindex 1, where A is some integer. And similarly, we do for groups G2 and the target group GT. And very importantly, we also have a bilinear map. So this means that although we have additive groups, we can actually multiply together in some sense elements from different groups. So we have A1 here and P2, then we can use pairing operation to get A times P in the target group. We will also be using polynomial commitment schemes. So what is a polynomial commitment? Here the committer sends some representation of a polynomial f of x, which is succinct. So it's smaller than the size of the polynomial itself. Then verifier can pick any integer alpha, and the committer will send f of alpha, and he claims that this is equal to some y, together with the proof. And the properties that you require is binding, which means that y is correct. Committer cannot cheat. Succinctness, which means that both the commitment size and the proof size are much smaller than the representation of the polynomial. And we also require homomorphism, which simply means that if you have commitment to f of x and commitment to g of x, and you add them together, then you get a commitment to f of x plus g of x. Now, what is the sum check argument? We already briefly saw it. So again, we have a prover and verifier. Prover knows a polynomial f of x, some value s, and the set h. Verifier knows commitment to f of x, again, integer s and h. And now prover claims that if you evaluate f on elements of h and add them together, then that's equal to s. So that is what a sum check argument is. And this is what we need, based on the previous scheme, to get CK SNARK for R1CS-like constraint system. So firstly, we know this a nice, very simple and nice lemma. So let H be a multiplicative subgroup of some field F. And let's denote the size of H by M. and let our polynomial f of x be some degree d, then the following relation holds. So if you have this sum over f, then that is actually equal to n, the size of the subgroup, times the following sum. You have fi's, so coefficients of f of x, and you add together those coefficients where n divides I. And that is actually equal to this whole sum. So this is not a very complicated lemma to prove. I think our paper took maybe 4 or 5 lines, but it's mostly to observe this thing. So now let's keep this lemma in mind and think what we can do with this. So, okay, this is our polynomial f of x. We want to add together, based on this formula, all the coefficients where the index divides by n. So this is f0, fn, f2n, f3n, and so on. Let's fix some integer d gap, which is larger than the degree of the polynomial. And then we want to do the following. We want to multiply f of x by some polynomial s of x, and we'll see in a moment what this is, such that the result is the sum of the coefficients where the index divides by n. So this is the coefficient of xd gap. Namely, if you look at this formula, then this is actually equal to this sum divided by n. N is the size of the group. And then for the rest of the coefficients, we don't really care what they are. We should still note them by g of x and let them be. So how do we pick this s of x? We can pick it as follows. First, you have x to the power d gap. Why this? Because if you take this value, multiply it by f0, then it will have get the polynomial xd gap. Similarly for the next one, xd gap minus 1. If you multiply this by fn x to the n, then again you get that this will become part of this xd gap, and so on. Okay, so we got this nice formula, f of x times s of x equals s over n, xd gap, and then some g of x, which we don't really care about. And now based on this intuition, we can construct a new subject argument that we call count, because, well, it counts. Firstly, here is the structured reference string. So we pick some random sigma, and especially if you take a look at this first elements in the first group, then these are just powers of sigma, but we are punctured at the point d gap. So prover essentially cannot use sigma to the power of d gap. So this is very important. So again, prover here knows f of x, s, and the set h. Verifier knows a commitment. So he knows f of sigma in group 1, and the claimed sum, and the set h. And set h here again is this multiplicative subgroup of some finite field f. So prover computes the polynomial just as we saw in the previous slide, this g of x. Then he will just send this one value in group 1. So he can compute this because g of x is missing this one monomial sigma to the d gap. So he can compute it. And now verifier checks this very same equation. And this is actually it. So here we get a subject argument which contains only one group element. So it's essential or optimal, at least in the number of group elements. So we proved the security of this argument in algebraic group model. The previous best subject argument was from Aurora's ZK SNARK. So here is the rough comparison. In the SR size, we are worse. We're about double. Provers complexity is somewhat hard to compare without an implementation. Verifiers complexity is the same, and in proof size we improved, but from 2 group elements to 1 group element. Okay, so how, what do we in the end achieve? So we have now a subject argument. From this, based on the scheme that I showed before, we can get an interactive, succinct zero-knowledge argument. Then on top, we will use some very aggressive batching techniques to reduce the actually the opening proofs used for commitments. And then we prove knowledge soundness again in the algebraic proof model, and we prove statistical zero knowledge. So this is zero knowledge without any assumptions. And finally, to get the ZK SNARK, we use Fiat-Shamir heuristic because our interactive protocol is public. Thank you for listening.
Are there any questions? Questions? There are no questions, so let's thank the speaker again.
Thank you.
And next talk, it's about SIDH proof of knowledge. A work by Luca De Feo, Samuel Dobson, Stephen Galbraith, and Lucas Zorbenik. And Luca De Feo should give the talk online. Luca, are you ready?
I think I
Yeah.
am. Can you see my screen?
Yes, great. We can hear you well. So
Okay, that's great. So thank you very much, and let's get started. So as you said, this is a joint work with a bunch of nice people from the University of Auckland, and we are all very sorry that no one could come to the conference. So we apologize for that. It would have been a pleasure to be there with you. So don't be scared by the title. This is titled SIDH proof of knowledge, but still there is something interesting in it. It's not broken. Not everything is broken, at least. And I'm going to explain what our goal is and what we can save after this terrible summer. So this is about proving knowledge of anisogeny. So in this talk, anisogeny will be an arrow between two letters E. Okay? E0, E1 represent two LT curves, and phi, which is the name I like to give to the anisogeny, is anisogeny between these two LT curves. What is anisogeny? Of course, it's a group morphism. It is an algebraic morphism. All these definitions that you may know or not. I will try to keep things simple and just do everything by proof by picture. So why do we want to prove knowledge of anisogeny? As you know, given two supersingularity curve, or more generally, given two RLT curves, it is difficult to compute an anisogeny between them in general. Then depends how you state exactly the problem. There are some easy instances and some harder, but the generic problem, just I give you two LT curves, find an anisogeny, it's difficult. And so, of course, if you can prove knowledge of an anisogeny between two LT curves, you're proving a non-trivial statement. From that, you can produce signatures. You can produce verifiable, whatever kind of primitive you can think of, PRFs, etc. Our goal, our main motivation when we started this work was to provide non-interactive key exchange based on SIDH. Now, this, of course, is something that's broken because SIDH being broken, you can't really hope for the non-interactive key exchange to be safe. But this is just one of the possible applications, and the protocols that that I'm going to describe still work and can be useful for other applications. And more generally, of course, the question why proving knowledge of isogeny is why not, right? You definitely, this is definitely a primitive that you need to use in many different occasions. So again, here is my problem. I have two LT curves, E0, E1, and isogeny phi between them, which I will draw as dash to signify that this isogeny is secret. It's the witness to my NP relation. And my goal is to provide a proof of knowledge of this isogeny. Everything I'm going to describe are going to be sigma protocols, so I guess I don't need to define details. There will be a prover, a verifier, and they will exchange a few messages. And in the end, the verifier will be convinced or not. When I say witness, when I say proving knowledge of an isogeny, I need to be slightly more precise, because what does it mean to prove to know an isogeny? If you've seen isogeny talks, you may have noticed that people use different ways to represent isogenies. Sometimes they talk about kernels. I will be talking about kernels. Sometimes they talk about group actions, all strange words. But let's keep it simple. So our language is the language of supersingularity curves. So I will give you two supersingularity curves defined over some finite fields, and two supersingularity curves are, by definition, isogynous. There is always going to be some isogeny between them. So proving knowledge of an isogeny will amount to prove knowledge of some witness, which typically we will represent as an isogeny walk. So you can picture this isogeny phi that goes from E0 to E1 as a sequence of elliptic curves that are along the way from E0 to E1. And the steps between these elliptic curves are, you can think them as small steps, and the long walk from E0 to E1 will be somewhat longer, a few hundred steps. And of course, each single step is very easy to do, but doing the long walk becomes very messy. So this, just to picture, to give you a visual realization of what we're talking about here, the dots represent some supersingularity curves in some small finite field, not the cryptographic size, of course. And the black path shows a walk between these two LT curves. So, stop moving. So you can picture some nodes to be closer, and then to other nodes, and these are the small steps in the graphs, and then you have some lengths that may be as long as a generic walk in the graph. We'll see that how long the walk is plays a role in these protocols. The important thing is that this is a representation that clearly takes polynomial space to write down, right? Because you just need to write the list of elliptic curves. Now, in practice, when we implement these protocols, we don't really write down the list of elliptic curves. That's not the most efficient way, but for understanding the theory, that's definitely sufficient. So let's start with a protocol that sounds obvious, but doesn't really work in general. So I have my two LT curves, E0, E1. I want to prove knowledge of the isogeny phi. I can start by taking a random isogeny psi to some other LT curve, and I will use the arrival curve E2 as a commitment. And then I can imagine a binary challenge sigma protocol where I get challenged with the bit 0 or 1. If the bit is 0, I will reveal psi. So this, of course, is unrelated to the secret isogeny. Doesn't reveal much. But of course, if the bit is 1, I will reveal something that's correlated to the secret, and it will be the composition of psi compose phi the opposite way, the other way. Now, this sounds like a reasonable way to do things. It's very similar to the classic rough isomorphism proof sigma protocol. It also kind of works in some cases. It works for C-side, it works for ordinary curves, more generally works for the whole framework of cryptographic group actions. And this is how isogeny-based signature schemes based on C-side are made. So you may know about C-side and C-fish. It even works more generally for general supersingular curves. And now C-side are supersingular curves, but they're not general. And we're looking for something that works in general. This is the catch. Galbraith, Petit, and Silva showed that if you know the endomorphism ring of E0, then you can do this kind of protocol with a binary challenge and like essentially drawing a commutative triangle. But again, knowing the endomorphism ring of E0 is not general. Plus Galbraith, Petit, Silva, it's not the most efficient protocol on Earth. And we're more interested in having something that works all the time and can run on a computer in a reasonable time. And this is something that's not known. We don't know how to make this kind of a commutative triangle in general for supersingular curves, except in ways that are trivial and that are not zero knowledge, which of course wouldn't be very useful. So there is one technical ingredient, and this is what's left of SIDH, I guess, at least in spirit. SIDH still lives in these commutative diagrams that we call push-outs. So instead of drawing commutative triangles, which are a bit complicated to make, we will draw commutative squares, which are very easy to construct using a generic construction that's called a push-out. So if I have an isogeny phi, could be my secret isogeny, and another isogeny psi, which could be my commitment isogeny, I can push one isogeny through the other. So for example, I can push phi through psi to compute some isogeny phi prime, which I will call parallel to phi. So being parallel is not like, it's something that's respective to a third isogeny, right? So phi is parallel to phi prime with respect to psi. And this in practical terms, in algebraic terms, means that the kernel of phi prime is the image through psi of the kernel of phi. When you do this, then you can also push the other way. You can push psi through phi, and what you get is an isogeny psi prime, which is parallel to psi, and the diagram commutes. So this is the general construction of a push-out, and the case where it's most useful and most interesting for crypto, and that's the case that was used in SIDH, is where the degrees of phi and psi are co-prime, so I can call them capital A and capital B. You can think of them as being a power of 2 and power of 3, like exactly, there's a typo there, doesn't have to be the same power of 2 and 3, could be 2 power n, 3 power m. So you can think them as being powers of some small prime, but all that I'm going to say works more generally, at least the basic principle. Then implementing it's a bit different maybe. As long as the degrees A and B are co-prime, everything works. Now, here's a protocol that intuitively should work, and that's a protocol that with David Zhao and Jerome Plut, we proposed back in 2012 when we first introduced SIDH. And the idea is, well, let's do the same thing as the commutative triangle, as the graph isomorphism, but instead of revealing 1 out of 2 possible answers, we will reveal 1 out of 3 possible answers. So I can construct, so let's say phi is my secret that I want to prove knowledge of, and I can construct the push out on top of some random isogeny psi and phi, and then I will get challenged with 1 of 3 possible challenges. So if I get challenged with trait 0, I would reveal psi. If I get challenged with trait 1, I would reveal psi prime. And if I get challenged with trait 2, I will reveal phi prime. This is almost the way it's described in the Feo-Zhao-Plu. Now, the Feo-Zhao-Plu explained how use binary challenges instead of ternary challenges, which made a lot of sense in the SIDH setting, but doesn't make much sense anymore. So let's stick to this example here. Let's stick to 1 out of 3 challenges. And now, I mean, this protocol seems reasonable. It's clearly correct. Like if you know the isogeny phi, you can clearly construct the push out, so there is no problem. And now we need to prove, of course, knowledge soundness and zero knowledge. And this is one where I things are a bit nasty. So this is the way that back in 2012, not 2011, we proved the special soundness of this protocol. We said, okay, let's say that there is some isogeny phi from E0 to E1. It is enough to know 2 sides of the square. So I can know, for example, the sides, the 2 sides in blue here. And then I can, of course, pull back the isogeny from E2 to E3 along the isogeny from E0 to E2, and then I will recompute the secret isogeny. So I can clearly extract from just 2 answers, 2 correct answers, I can clearly extract the secret isogeny. The same would work if instead of the one from E0 to E2, I had the isogeny from E1 to E3. The only one that doesn't work is having the two parallel isogenies that go from E0 and E1 to E2 and E3. Now, this seems reasonable, but it's of course wrong, because when you prove knowledge soundness, you need to assume that you have a cheat improver. And now the cheat improver does not necessarily even give you a pair E0, E1, which is in the language. It is totally possible, it happens, and it has been remarked a couple of times just this past year, that given the SIDH parameters, it is not obvious that there is an isogeny from E0 to E1 of the right length, an isogeny walk of the right length. So we may be in a case like this, where the sides are not really parallel, and then you have no way of knowing whether there is a witness. So if there is not even a witness, how can you even extract it? So there was a flaw in the proof. We were making some wrong assumption. This was only noticed very recently. And so what we did in this paper is essentially fix the soundness issue. And now I'm going to explain what are fix, which you may think of it as being elegant or not elegant, depending on your tastes, how our fix works. So the idea is to, again, get some SIDH flavor and use some torsion point information to force the diagram to exist, to force the sides of the square to be parallel, so to really have a square. So the idea is that instead of committing just to elliptic curves, we will commit to some torsion basis or some level structure, if you like. So we'll take random torsion basis P2, Q2 of the B torsion. So this B is the same as the degree of the isogeny that goes from E0 to E2. And so this will be useful to describe the kernel of the isogenies of the vertical isogenies, psi and psi prime. We need to commit to something else. We need to commit to a pair of integers A and B, whose role is going to be clear immediately. Now, let's construct the usual commutative square on top of this E0, E2, E1, E2, E3, and now let's describe the protocol. The protocol is again going to be a 3 challenges protocol, 0, 1, or 2, and depending on what treat I receive, I will give one answer. So the first answer I can give, let's start, for example, from a challenge, from being challenged to reveal the bottom isogeny. So in this case, I can open the lower side of the triangle. I can reveal phi prime. But I will also open my commitments. So the gray boxes here represent some statistically hiding commitments, so that I can see what's in the gray boxes only when I open them. And so now what I have in red in the bottom is the equation that the verifier needs to check. So the verifier will check that the basis P2, the basis P3 Q3 is the image of the basis P2 Q2 under the isogeny phi prime that I just revealed. Let's look at the other two openings. When I get challenged with revealing the left side of the square, I will reveal the dual isogeny rather than the isogeny. I will reveal the isogeny that from E2 goes to E0. So anyway, when you have an isogeny, you can always think of it as going both ways. It's computationally the same thing. And so in this case, what I will do is that I will open the commitment to the torsion basis P2, Q2, and I will also open the commitment to the pair of integers A, B. And what the verifier will check is that the kernel of psi hat, the kernel of the dual of psi, is the linear combination of P2, Q2 described by the coefficients A and B. And finally, for the third opening, when I get the challenge with the third possibility, revealing the right side, I will do exactly the same as the left side. I will open the pair AB, I will open the torsion basis, and I will check that A times P3 plus B times Q3 is the kernel of psi prime hat. Now, from this, it is finally easy to prove extraction. We can prove knowledge soundness. How do we do it? Well, it's again about pushing isogenies and pulling isogenies through other isogenies. So if you have these 3 conditions that I have in the bottom, the first thing you can do is that you can pull back phi prime hat through phi prime, which will be exactly equal to phi hat. So having these stronger constraints on the torsion, having this torsion basis P2, Q2, P3, Q3, and the fact that the kernels are the same linear combination of the torsion basis, this forces the vertical isogenies psi hat and psi hat prime to be parallel. And so this means that the kernels are the push forward one of the other. And this means that because of the general theorem, once you have two parallel sides, the other two sides also are parallel. So this means that you can push forward phi prime through psi hat, for example, and you will finally extract the witness that you were looking for. So by rigidifying a little bit the structure using this torsion basis, finally we have what we want. We have an extractor for our witness. So problem solved. This protocol is knowledge sound, and it proves knowledge of an isogeny walk of some length. Now we need to look at zero knowledge. Well, this is pretty easy. Simulating the two vertical sides, that's straightforward, because to simulate the left side, for example, I can just pick a random isogeny psi of the right degree, a random torsion basis P2, Q2, and then I will compute a linear combination AB that makes A times P2 plus B times Q2 the kernel of psi hat. So this is straightforward. Same for the right-hand side. And well, here is where we have a problem, because this is actually quite hard to simulate. The isogeny phi prime parallel to phi, it's something that's non-obvious if you don't have access to the witness. And actually, this is an assumption. So what we do for simulating this is just that we pick a random supersingularity curve E2, and then we pick a random isogeny of the right degree phi prime, which is not necessarily parallel to phi. And we make an assumption, which was already an assumption back in the Feo-Zhao paper, that this distribution is hard to distinguish from the right distribution, the distribution of pairs phi and phi prime of parallel isogenies. And this is called the DSSP problem. And it's a strange problem because there's a sort of SIDH flavor, so you feel it may maybe be broken, but actually it's right at the limit where we don't know how to break this assumption. Just a word on recent progress that's not in the paper, that's appeared recently on ePrint. There is a way to get rid of this DSSP assumption. So the problem is I want to distinguish between the right distribution, the correct distribution that's on the left, that's the distribution of parallel isogenies, phi and phi prime, from the distribution of random pairs of isogenies, which may not be parallel. And the trick in this paper with a list of others, which doesn't fit in a slide, is to just walk a little bit longer and longer and longer. Because of the properties of Ramanujan graphs of supersingular isogenies, it turns out that the longer you walk, the more this distribution will converge to the same distribution. So the way you can do it in practice requires lots of algorithmic tricks, but if we want, we can get statistical zero knowledge instead of relying on the DSSP assumption. However, when we do this, we cannot do anymore the trick with the torsion basis, so our knowledge soundness is not as good as anymore. So we still are in a kind of space where we don't know how to get all that we would like to get. Okay, so just to conclude, what we managed to do here is a knowledge sound computational ZK protocol for proving knowledge of an isogeny of some fixed degree or some fixed walk length, if you like. In the paper, we also have a variant to prove knowledge of an SIDH secret key, which today is not anymore that interesting, but I mean, could be useful someday, who knows. For the future, if you have ideas how to prove statistical zero knowledge with strong knowledge soundness guarantees, that would be a very nice result. Also, if you know how to make these things efficient, we're still at not so good. And finally, I showed something that worked for the general supersingular case, and which is not super efficient, but you can run on a computer. But something that still we don't know how to scale really well and to make really well is the seaside case. As I said, for the seaside case, you have the easy protocol, but that's actually not very efficient. Like if you see fish is cool, but you cannot really instantiate it for many parameters. And csign works in general, but kind of sucks. So we're still in a space where it's a bit difficult to prove knowledge over all kinds of isogenies. Okay, thank you very much. Ready for your questions.
Thank you, Luca. Are there any questions? No, it seems there are no questions. Thank you again for the talk. And
Thank you
this
very
ends
much.
our session.